So it seems that the broadcast has just started, Radek. So I hope I will close this window and that window. Yeah, hopefully we are on air. Not yet expert on air, but will be soon. I have one expert here, but let's wait. Let's give it. Yes, it's 2 p.m. on my clock. So yes, yeah, yes. So let's give it last few seconds and we will start the webinar. People are here, so we are not alone. That's great. And yeah, and more are coming. That's great. That's great. I always love to talk to more people. Yeah.
Than just to a monitor, right?
Yes, right. Yeah. Yes. So, so we will start very soon. So the webinar is being recorded. The recording is running well, and yeah, I need to close this. I guess I will make this full screen. And what? This is the next slide. Yeah. So I think it's time. It's time. So we will start. I'm starting it actually right now. Hello, everyone. This is Luboš Prikl from CFD Support, and I would like to welcome you to webinar, where we would like to show you a couple of things, actually a workflow, how to run external aerodynamic simulations, and I hope we will all enjoy it. So today I'm here with my colleague Radek Máca. Hello, Radek.
Hello, Luboš. At least I will enjoy it. So
that's great.
Hello, and hello to the audience. Great to see you here.
Great. So it's two of us. Some technical information about the webinar as usual. So the webinar is being recorded, and yes, the recording will be later publicly available on our YouTube channel, or there will be certain links how to view it. So yeah, so everyone hopefully is going to enjoy it. You do not need to to catch all the details because you can view the recording in your leisure time. What else? Yes, so in the first part there will be I would say introduction where I will quickly introduce what's going on, what's on the table, and in the second part Radek mainly and me, we will introduce the workflows. We will show a quick hands-on session, how to run simulations. We will show some tips and tricks, and we will do our best to share our experience and knowledge, and hopefully you will take away something from it. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions, and we will do our best to answer them. The most representative questions for the wide audience will be answered right away, still in the webinar. Specific questions will be answered later via email, but you can be sure that all the questions will be answered. And I hope this would be it. Please ask your questions anytime during the webinar. There's a window for it, so use your chance. You use really this opportunity to ask, and we will be happy to answer. That's important. So ask anytime, and we'll do our best. Yeah, and otherwise, yeah, make yourself comfortable and think what you need for your simulations and ask, and that's it. So Radek, I think it's time that we will switch off the cameras because yeah, we will come back later. We are still here actually, but we will close these cameras because we believe that the screen ratio and ratio of important information versus non-important information will be better from now. Okay, so yeah, so the external aerodynamics, it's pretty much everything. We will where the object is exposed to flowing air with somehow kind of open boundaries. So it could be wind or it could be a moving object exposed to the flow. So we will talk about it in today's webinar. And of course, you know, we do a lot of stuff, a lot of simulations and a lot of things. There will be other webinars. So we would like to invite you to next webinars. So there will be, next webinar will be about centrifugal compressor. The next one will be about Francis turbine. Another one will be about the acoustics and also about wind turbine, and blood pump will be the last webinar of this year, I think. So CFD Support is the name of our company. We are 15 years on the market, and we deal with computer-aided engineering, which specifically means CFD, FEA, and FSI, optimization and acoustics. Those are our, I would say, main fields. Based on our previous projects, we are especially focused on turbomachinery applications and external aerodynamics. External aerodynamics is topic for today's webinar. Our I would say flagship product is software. So we do both consultancy and software, but software is our, I would say, the main flagship product and thing what we deal the most with, and it's called TCAE, and it's fantastic software where you can do everything. You can do a lot of simulations. There are a lot of options. It's extremely usable and easy to use. It consists of software modules. There are modules for example, for meshing, for CFD, for FEA, FSI, and for optimization, also for acoustics, and other modules are being developed and still to come. TCAE is extremely flexible. It fits any existing workflow, or you can create with it a completely new engineering workflow. It depends on your effort, on your goals, on your skills, experience, knowledge, anything what you need. TCAE is extremely flexible. It's ready to fit workflow with other in-house codes, or I mean with other open source codes, with existing commercial codes. It's really great to fit in workflows. So it's definitely very modern software. It's unlimited. It means there are no limitations on the number of its users, jobs, cores, hardware installations. It's ready to help users to scale their resources to the fullest. It's very important. It's focused on, as mentioned before, it's focused on turbomachinery applications and external aerodynamics. It's it's dedicated to these fields. It's well automated. There are a lot of benchmarks we did in the past. There are a lot of tutorials, and we have really good technical support. So maybe we will talk about it later, but the software is one thing, but the knowledge transfer to the users and the way how to use things to receive reliable results is the other thing. So it's definitely software is one thing. And knowledge transfer is other thing. We are offering both in this with this. It's very important. The way of use of TCAE is again very wide. So you can use it remotely. You can use it, of course, sitting at your computer, at your laptop, desktop, PC, cluster cloud. You can work remotely from home or from work in Linux, in Windows. It's basically there are endless combinations of using TCAE. It consists of open source. That's very important part. It's our DNA is using open source, and to turn it into something better, which is usable in the industry. That's very important. So based on these more than 60 open source projects, we have developed and worked more than 40 many years aggregated here at CFD Support to deliver this software. So you can imagine how much work has been spent to deliver such a piece of technology. And that's what we are showing here. We are always in progress. We are moving all the time. So in the future we'll be more and more developing the optimization part, which is extremely important. And in a way, it's a future of simulations. So it's not just guessing the best scenarios, but really finding the space of optimization functions. So finding the best possible is the optimization, is the future, one of development things here. We also dedicate a lot of time to development of acoustics module. It's again very much, I would say, high-tech technology. So the acoustics, another part. We are developing a new module, which is called T-based. Everything will be written down, and based on it will be surrogate models. And finally, a very hot thing is we are developing new product, which is light version of TCAE. It will be accessible for literally for everyone. Everyone can use it. Everyone can allow it. It will be cheap as hell, and I'm sure everybody will like it. So new TCAE Lite will be released soon. You can look forward to it. It's really great thing. Okay, I think this was quick, and I'm happy for that. I did not do much harm here with the introduction. So now we will, and Radek, I will need your help certainly. we will show you a couple of principles, tips, and tricks, and our well, I would say, yeah, our some opinion about how to do the external aerodynamic simulations. So I will slowly start this time. We have a little modification. We will start on my computer, and I'm going to a little example I have prepared here for you. By the way, Radek, can you confirm that you are following and you can hear me still?
Yes.
Okay, I'm glad.
We
I'm
can
glad.
we can see
Yeah. Okay,
your
that's great.
screen,
That's
and
great.
I am here to support you.
That's perfect. That's perfect because I think that I will run out of my ideas very quickly. So hopefully you will come and save me and take over. Okay. So today's topic is external aerodynamics. Specifically, we have prepared a Formula One model which we would like to show you. We would like to show you how to simulate it. I hope you can still see my screen. So this is Formula One, which by the way, it's Audi, right? Our favorite model. And this one is pretty, it's nice. I like it so much. It's 80 years old. And this is how the Formula One, started, but basically. It looked like this. So it was like 4 wheels, some kind of body, or really nice boat or something with large 16-cylinder engine in it. Really nice. And it was just pure power on 4 wheels. Everything relatively simple, as you can see. Yes. And then, and this is a point I wanted to make, is then the CFD engineers came, right, and created something a little bit different. And over these 40 years, it turned into something as complex as this, which is a relatively recent model of Formula One. And we can pick which one. So for today's webinar, I will pick for you. I will pick the new one. But so the takeaway number one, or lesson number one of today's webinar is, don't believe CFD engineers, right? Because they make everything extremely complex, extremely complicated, and then they ask money for it. No, I'm joking. It's this formula. Let's play with it. It's extremely complex. There are really a lot of components which are not visible all the time, but we will show you couple of how to make a simulation. So I will start with let's say fact that you will need a model. You will need a 3D model, and in the beginning, the only, it's not very little, but the only requirement is you will need to have it waterproof, because you certainly would like to create meshes where the inside is completely divided from the outside, right? Because you do not want to, if you put the water in it, the water should stay in it. There should be no holes. Otherwise, you would be, when you will be meshing the model, the mesh would be created from the inside, which is certainly something you do not wish at the moment, because it's a waste of, at least it's a waste of computational power, if not accuracy and stability. But yes, you need a waterproof model. Am I still understandable, Radek?
Yes, fully understandable.
That's
Just go ahead.
Thank you very much. So I'm going ahead. So so a model, right? You need a model, and you need to make it somehow waterproof, which is sometimes complex task. Sometimes it's not easy, but it's something you need. It's not this condition is requirement is not completely compulsory. It's definitely not that critical as in the internal aerodynamics, like turbomachinery. There you definitely have to have these waterproof components, but it's strongly recommended, I would say. So strongly recommended to have waterproof waterproof these models. Okay, and when we talk about the external aerodynamics, we almost always put this object into what? Into this virtual tunnel. We call it virtual tunnel, which is a box basically, where we say, okay, the object is typically it's moving, but to simulate the movement in this Eulerian space, we say, okay, let's do it. To make it a little bit simpler, we will keep the object steady, and we will flow with the air around, and this relative movement of the air around instead of the moving object in the air is it works. It's with many years it has been working. So we are moving, we're flowing with the air on the object, and there are only very little differences and very little inaccuracy which is coming in. Yeah, of course, it's I know you know it. It's the turbulence and turbulence intensity. But anyway, this is how the simulations are done. You put your object in the box, and you let the air to flow around it. So yeah. So basically in TCAE, because TCAE is what we are talking here about, you need to create the volume mesh, as you know, and so you load this model into the software environment, and you see a little table where you specify, you specify the bounding box. So you say what points are defining this virtual tunnel, which it's completely up to you. Some people say that bigger virtual tunnel leads to a little bit more accurate results. So but in the beginning we like to take it simple, play simple. So maybe this is a lesson number 2. I would like to recommend start with simple models. And also another important point is that not that many settings or that many knowledge is necessary in the beginning. So you can receive relatively accurate results with only very little knowledge. Yes, every workflow and every CV simulation can be as complex as hell. That's right. You can play everything. There are hundreds of parameters and everything. It can be extremely complex, that's true, but with only very little knowledge, and that's the purpose of today's webinar. We would like to show you this minimum to be able to run relatively accurate results. And from some level, it starts to be extremely complex, and you for a lot of work you receive only very little value. So we would like to help you with this to get a lot of value with little effort. Okay, so in the beginning you put this in the box. You say what is the box. You say these points. And because TCAE uses OpenFOAM on the background, and it uses snappy hex mesh meshing because it's natural, not very natural, and very usable automated meshing tool for complex geometries. It's extremely usable and effective. So you need the mesh. So you say, okay, here are my refinements. So you say how much you would refine on your model, which is called F1 full, and you say what are the refinements. You say what's your basic mesh. That's important. So it's the largest cell in the volume mesh. You say its dimensions and let it refined in the direction perpendicular with respect to the surface, and it gets divided a couple of times, depends on your settings, and that creates your volume mesh. I know it's very condensed information, but in this webinar that's what we wanted to. So you create the mesh with a couple of settings, but it's not that many settings. So you say the basic cube. In the virtual tunnel, you say how many times it should be refined, minimal and maximal, to which surface. You can have as many surfaces as you wish. You say where is the internal point located. That means it decides what's the inside and what's the outside of the mesh, and that's pretty much it. Then you can let the mesh get created. So you create the mesh with clicking build a mesh, for example. It gets created. I did it just like 20 minutes before the webinar, and yes, the I would say the rough mesh is created is very simply. So this is for an example of about 1 million cell mesh. So you could see that it's relatively, yeah, I don't know what it is. It's definitely very rough, but you will receive not bad results on it, and definitely results which are simulated on this computer I'm sitting at is relatively old. Yeah, it's actually 10 years old computer, and it still in 1 hour gets this 1 million mesh gets simulated. So my point is you can have quite quickly quite good results. Yeah, so that's the simulation mesh. Now I'm talking about the volume mesh, right? Those are cells everywhere in the virtual tunnel, right? So this is just the symmetry plane of the virtual tunnel we are looking at now, and you can see how the mesh is refined, and what is about 1 million. So it's very coarse mesh, but yeah, usable, definitely usable for the webinar. So well, so it's the mesh settings. So you can, if in the beginning you need to do just a little settings, right, which is those 2 or 3 parameters in the mesh, and then you need to do some simulation settings, which is for this we use this TCFD module, right? So there are modules. So T-mesh is for meshing, TCFD is for the CFD simulation, and again there are only a few parameters you should play with. So for example, this computer has 16 cores. So you can say number of processors you want to use. Then the default settings is very simple. So the simulation is steady state. But yeah, this is very important decision. Steady state simulation. The fluid flow is the air. You can keep everything as default. There are yeah, quite a lot of settings you can play with, but there are only few those settings which are important. That's my point. So it's definitely a number of processors, maybe the order, the numerical scheme order, and then you may say what's the yeah, what quantities are being written down during the simulation at the external aerodynamics. It's typical we use these forces acting on the body. In this case, it's the Formula One. So you can yes, say I will use this forces object, which helps to evaluate all the forces and also the coefficients like drag coefficient, lift coefficient, or momentum, etc., etc. You can set probes in the field, and what is extremely important is the boundary conditions. So I will go to boundary conditions because its boundary conditions are what defines your task and what defines your simulation. It's extremely important. So there you say, okay, I'm flowing with the air to the virtual box. In this case, we have 50 meters per second, which is the velocity at the inlet, and at the outlet we specify something like fixed pressure. And this is basically it. This is basically it. If you do such a little settings, it would work. And yep, the simulation can be run, which I did again a couple of minutes ago. So I could continue here. So simulation has finished after about 1,000 iterations, and maybe I could show the results if they're already written down. So let me see. The simulation has taken. Let's take a look. There is a report which I should mention. So every simulation has its report, which tells what tells the details about about the mesh, for example, how much cores have been used, how long the simulation has taken. So you can see that 1 million mesh, which is quite coarse, has taken 18 minutes. That's not much. And yeah, I haven't any more details. Yes, I know why. So that's not important. So I'll go to the volume results if they're available. Hopefully it's there. And in the meantime, I will ask my colleague Radek. Radek, is there anything as a follower? Is there anything you would like to see here? Something important I didn't say?
Well, until now, because I'm too much in it,
Right.
and I do it every day. So
yeah, yes, yes, I understand. Okay. Anyway, yeah. So yeah. I wanted to make it simple, but sometimes it's a trap, right? Because there is a lot of information,
definitely.
and sometimes it's very difficult to make some condensed information out of it, right? Because we are, sometimes all of us are too much in it. But anyway, this is the these are the results. What I wanted to show. This is the surface which has been used, the 1 million mesh actually, and yeah, so this is the pressure field. So this is the, yeah, these are the how the pressure can look like. By the way, the ParaView is which is used as graphical interface for TCAE is fantastic post-processing tool. There are a lot of options everywhere. There are a lot of filters. There are a lot of sources. There are a lot of functions that can be used for post-processing. You can play with it. You can make animations. You can. It's really really great tool for post-processing. And yeah, basically here you can play with the results and all of them. And here you can learn, and then here you can make your models and make your simulations and guesses and engineering stuff more accurate. Maybe I'm a little bit out of my ideas what else to say, because there are a lot of things we could talk about. Maybe this is the time, Radek, that I would ask you to switch over to you.
Yeah, sure.
And then we can,
yeah.
Yes,
Maybe keep
yes.
the results here, and maybe some question will arise.
I will
and
keep everything
then
open.
we can
Absolutely.
go back to the
I
visualization,
will keep
for
everything
example.
open. Yes.
Yeah.
And
So,
again,
so
I would like ask the audience to ask your questions. We will be happy to. You will help us. You will help us to save this webinar to really answer. So yeah, we'll be ready to. We'll be happy to help. And Radek, I think we can see your screen. So maybe.
Okay, great.
You can go.
So yeah, thank you, Luboš. So Luboš showed us how to play with the complex shapes to simulate in the framework of external aerodynamics. So just to emphasize that the main thing is to have a nice, ideally waterproof STL model, and then if you have the model with a good quality, then you can just put it into TCAE, pretty quickly set up the meshing part, then adjust the CFD simulation, and you can pretty quickly get the first results, which could be accurate enough to have some kind of overview of aerodynamics parameter of your object. So now I will move to a more simpler shape. So I think all CFD engineer in the past play with the aerodynamics of a simple aerofoils, which is, I think, one of the first tasks even during the studies, to play with the aerofoils and some kind of study the dynamics, evaluate the drag lift coefficients, compare with some measurements or other software results to see how the CFD workflow in general works. So maybe I would like to go to this application to just study the aerofoils with a very simple shape, and maybe to show some kind of advanced application to study, for example, or to study the drag lift coefficient with respect to the different angle of attacks and how to run it by a single click. So also this is possible in TCAE. You can prepare your CFD simulation, and by the TOpt module you can parameterize and almost everything, and you can run a nice analysis for wide range of application or parameters and get very nice analysis. So let me quickly show you how this workflow can be created. Okay, so how I will start. So at the beginning, what I would like to do is to create a mesh, or from some kind of aerofoil profile. So I will take one of the easiest one, this NACA 0012 profile. Typically you get this profile by some coordinates, and from these coordinates you need to create the geometry. From the geometry you can create the computational mesh. So for this task, I use this simple construct 2D program, which is a simple program, I think, written in Fortran, which works, which you basically just put the coordinates of the airfoil, of the general airfoil. Then you put some kind of parameters of the construct 2D. Basically, you will just define how many points will be divided along the surface in the normal direction from the surface. If you like to use the O grid or C grid, some kind of spacing or spacing to the or expansion ratio to the leading edge or to the trailing edge, dimensions of the the whole flow domain, many other parameters, and it will give you a mesh in simple plot 3D coordinates, which can be then, for example, transformed into the OpenFOAM format and directly load to the TCAE, or you can prepare some kind of STL from it, put it into the SnapX mesh. But in this scenario, I would like to show you a very simple example on a 2D mesh. So the SnapX mesh is not the best for creating 2D meshes because implicitly it works in 3D. So many cells are created, and then maybe you can just extrude it, the symmetry part or the empty direction to get the 2D mesh. But it's more complicated, and this construct 2D, which is open source, can be used very effectively in this application. So what I would like to show you, yeah, this one. So I have created in Linux, but similarly in Cygwin environment, when you compile the construct 2D in the Windows, then you can use it in the same way. Let me just quickly show you how the mesh is created. So first I will run the construct 2D, where the input is the profile text file. Then we put the construct 2D parameters, as I have shown as a latest file, and this basically creates a P3D format of the mesh. And then in OpenFOAM, there exists plot 3D to foam command, which you put in these options, and it will generate you the mesh with a thickness of one cell, and this thickness you define, I define it as 1 meter to have 1 meter length and 1 meter span, which gives me this reference area of 1 meter, which is a typical dimensions to be set for analysis of the airfoil, because then you have a nice scaling, and then the evaluation of direct lift coefficient is more straightforward. Then we do some modification, because implicitly it includes just a single patch for all the parts, but I would like to split it to define inlet, outlet, etc. So then there is kind of auto patch command, which by degree it will divide you the patches which are connected by the given angle. Basically, if there is an angle larger than 85 degrees, then it will split the patch to the more patches. So this number will give me exactly the splitting I want, and then presetting by create patch, it will give me a nice final mesh with all the patches named properly. So let me show you what is our output of this mesh preparation with external tool. So if I denote just all the patches to see them. So this is the topology of my mesh. You can see that all the patches are splitted. And when I visualize surface with edges, just to see the topology, and let me just focus the view on the proper view. I switch to 2D and scroll inside the flow mesh. We can see the NACA profile and the mesh topology around the blade. So for such easy shapes, this structured hexagonal mesh is the best you can have, both both with respect to the generation and the accuracy. So this is a very nice mesh and is 2D. So let me show you that if I zoom, that there is just one cell in this Z extruded direction. In the similar way, you can extrude it with more cells to create a 3D mesh. But for example, if this mesh has 50,000 cells, I guess something like this, and you extrude it 100 cells in the Z direction, then you will have, quick counting, 5 million cells. Yes, 5 million cells mesh, which is then more computing demanding, but for example, to fully study all aspects of the turbulence and so on, you need to go to the 3D. So the 2D cases in a turbulence mode is some kind of pseudo simulation, because the real flow has the 3D properties, not the 2D. There is no symmetries in all the eddies, etc. So this kind of simplification, but for some scenarios, it will give us a nice guess about the airfoil and aerodynamic coefficients. Okay, so this will be the input for my TCAE. So let me quickly show. Okay, so I will close. I will open the empty TCAE project, and I will show you how maybe in 5 to 10 minutes we can preset a CFD simulation when we have the mesh ready for it. So let me open the empty one. So I will create an empty project. Empty project is created. I will save it somewhere into my working directory. So TCAE live example, for example. So I will store it here. And now let's go for setting the T-mesh. So in the T-mesh, in this case, we just load the external mesh. We preset the type of patches. So let's go for it. So I will click on the item T-mesh. Then when we go step by step quickly, we don't need any rotating reference frame, so I can get rid of it. We will have just static frame. Here we have one component, and here we will import the volumetric mesh in OpenFOAM format. So I will go to 2D mesh. Now the generated 2D mesh is loaded directly. So if you go to the CFD geometry, which is in this case the ready to simulate mesh, so we can also see the topology of it, and then we can call it component names, just like the flow domain. If we want, reference frame is static because we are going for static simulation. No moving objects will be included. And now we just preset the type of the boundary. So airfoil is a wall, back and front are the basically front and back faces, which will have the empty type. So in this scenario, we just tell it that in this direction, there is one. This is the 2D direction, so we don't need to solve any equations for this Y direction. Inlet we set as the inlet, and outlet we set as the outlet, and we are done in preparing the mesh. So I can save my setup. So these were the only steps I need to perform to import the mesh for this kind of simulations. And now we can directly go to the TCFD setup and preset the TCFD simulation. As Lubos already mentioned, there are just maybe 10% or 5% of all parameters available, which we need to go through and fill for these kind of simulations. So first one is the simulation type. I can switch to stator, or maybe more or less it's kind of virtual tunnel simulation. Time management, here we set how many speed lines. So we would like to simulate just a single boundary condition, so single setup, single mode, for example, fixed velocity and given direction, or velocity which corresponds to the given angle of attack. So let's start with 2000 iteration, for example, as the maximum. Oh, sorry, this is speedline point. Sorry, I need to go here. 2000 iteration, fluid properties. We will simulate the low speed aerodynamics, so the speed below 0.3 Mach. So we can stick with incompressible solver. I will stick with the fluid default, but if you would like to simulate the airfoil at given attitude or whatever, so you need to adjust the dynamic viscosity and, for example, pressure reference density to your conditions of the flow of the fluid. Rotational reference frame, it's not applicable here. Multiphysics, we don't need to switch anything. Turbulence model, we stick with the default one, K omega SST. When we go to the simulation, so here in the solver, I just adjust the 10 processor, which I have on the computer I'm sitting at. Numerical order, I'm confident that my setup will be okay, so I will switch directly to the second order scheme. Runtime evaluated quantities, so averaging window I can keep to the default. Here I can, for example, ask for computed wall shear stress, which can be useful information about the aerodynamics and about the results. And for example, I would like to also ask about the compute pressure coefficient. So I would like to evaluate on the airfoil and reference velocity. I am planning to simulate, for example, 15 meters per second. I think it will correspond to something Reynolds number like 1 million or something like that, with respect to the dynamic viscosity we set here and the length of 1 meter of the airfoil. All right, efficiency pro, I don't need it, but forces, this is what I need to evaluate. So I would like to evaluate the forces on the airfoil. Lift is in the, let me zoom it. Okay, so lift direction is the Y direction, if you can see it here. So I need to switch the lift to the Y direction. Drag is in the X direction, and the pitch, which is for the momentum, is in the along the Z axis. So let me switch to Z, and torque is the same, but can be evaluated at different points. And center of rotation, maybe I can set some like of 1/3 of the chord of the airfoil. All right, and last parameters to set is the reference area and reference length. Because I have extruded the airfoil, which is 1 meter in chord direction, and the span is also 1 meter, so reference area is also 1 meter. Reference length is 1 meter, and reference velocity will be 15 meters. This is what I will set as the inlet boundary condition. Then we can go to the convergence check. So because I would like to study the drag and lift coefficient, so I can go or ask to check the convergence based on the force probe monitor, and the particle quantity will be the averaged lift, and the same for the drag, for example. So average drag, absolute tolerance, maybe because drag and lift changes. For example, for zero angle is basically 0, and for angle like 15 degrees or something like that, the lift goes up to 1 or more than 1. So I would like to, for example, stop the simulation whenever relative convergence value will be 1%, which means 1% to the current value of lift and drag. And if the instant value oscillates less than this tolerance, then the convergence triggered stopping the simulation before the maximum iteration are reached. Then we can go to the controls. This you can keep as it is because it's set to the defaults. Maybe check just the field bounding limits. So this is the limits to the minimum and maximum pressure allowed, typically just to cut off some unphysical values. So I will put something like -200 Pascal plus 200 Pascal to be extremely sure. Maximum velocity 1000, that's pretty enough. And now we just need to set the inlet and outlet boundary conditions, and we are almost done. So if I set, for example, the free stream velocity would be the best, because then when I change, because my inlet is basically half of the circle and a half of the circle is outlet, and when I would like to set some kind of positive or negative angle of attack, I would like to I don't want to care what is the inlet and what is the outlet. And for this type of simulation, we can set this free stream boundary condition, which automatically switches between what is the inlet, what is the outlet, based on the free stream velocity value and direction. Because I am in the incompressible mode, I can set the free stream pressure as relative as 0 pascals, and free stream velocity will be, for the beginning, 15 meters per second. And the turbulence quantities, you can put it into any table based on the turbulence intensity and turbulence viscosity ratio or whatever. I think for these conditions I have calculated something like this. So 1 for turbulent kinetic energy and 5,000 for turbulent dissipation rate. For the walls, you can switch, you can set basically the no-slip wall function. I need the airfoil with friction, and depending on the resolution of the refinement, you can stick with the standard wall function for Y plus around 30 and more, and for less Y plus, the best is go up to the 1. You can switch to the low Reynolds wall function for the resolved walls or resolved boundary layer. So I think it's not so resolved, so I will stick with standard wall functions. Initial conditions, you can just follow the conditions at the inlet. So I will set it to follow the condition at the inlet to have a nice initial gas. And for the post-processing, you can adjust the units and the report section, which will then appear at the end of the simulation. So for this type of simulation, I just basically need the force coefficient, because other quantities are not applicable here. Maybe, okay, velocity magnitude, but it will correspond to the inlet velocity boundary condition, basically. All right, so keep me fingers crossed that I have set everything properly. The other are some kind of advanced post-processing tools, how to save the result and store it for application in another codes, for example, but we don't need it at the moment. So I will save it, and we can run all buttons. So now it will just import the mesh we have defined, and then it will run the CFD simulation if everything is set properly. Now we can see that the simulation is running. Here we can see the residuals, and you can open new line chart view to also follow the quantity. And when you click on this window, go to the display, get rid of everything, you can just enable the CLCD values to be visualized. And I need to get rid of the mass flow, which is the default one, I guess. And now we can see the values of the instant values for drag and lift coefficient. So I will zoom it to something like this. Okay, the lift should be 0, and drag should be something about 0.01 or less than 0.01. So we can see that it converges pretty quickly, because yeah, the angle of attack is 0 at the moment, and so on. So you can see that I was able, okay, maybe within more than 10 minutes, I was able to set up such a simulation. And just to extend this workflow, so for example, I would like to see a map. It is like here, for example, I would like to see the drag and lift coefficient with respect to the angle of attack, something like this. For example, this Reynolds number 1 million. So how to do it? Okay, you can set 10, 20 separate simulation, separate project, and for each simulation, you need to change the inlet condition. So you need to transform the free stream velocity vector by the given angle of attack, and because you change the direction of the flow, basically you need to also adjust the parameters of the lift and drag directions. Yeah, so this is pretty tricky to do it manually. So basically, for any different angle of attack, you need to adjust the lift and drag coefficient to follow the rules of evaluating drag and lift coefficient. But with what you can do, you can enable the T-opt. Oh, no, this is not, this is the prepared one. Yeah, this is the current one. So you can enable the T-opt. Sorry, I need to go up here, enable the T-opt module. And inside the T-opt module, you can define something like, let's say operation mode, it doesn't care, but this is DOE for now. And we add a custom optimization parameter, which will be, for example, angle of attack, which will be the real type, linear space, minimum will be, for example, 0, and maximum will be 15 degrees. And the tracked quantity will be the built one, lift, and, for example, so drag coefficient and the lift coefficient. Where is it? Lift coefficient here. I can rename it to follow the standard abbreviation CD, CL. The maximum is something because, for example, I would like to also simulate the negative angle of attack. Here, positive should be 0 up to the, let's say, 1. And this is the accept range. When the simulation gives these parameters out of the range, then the simulation will be excluded from the set of T-opt simulations. And then what is important, and here's the trickiest part, but you need to create an initialization script which somehow connects our parameter angle of attack with the simulation itself. And let me describe it, how this is done. So if I go to my preset case, which I run in advance, which is here. So everything is set in the same way. So I have angle of attack, I have track quantities, and because here I try to run the optimization mode, and my optimization function is, for example, lift to drag ratio, and I would like to find the maximum of the lift and drag ratio. So the results of this kind of simulation will be the angle of attack for the airfoil NACA 0012, which gives me the best CL/CD ratio, the highest one. And to do this, you need to implement this initialization script, which is the Python script, which can basically manage and connect any external tool. You can compute any of your own formula to somehow influence the optimization mode. And I would like to just tell you how to, or base principles. So what I do here is that I read the speed value I have set. So I read my X component of the inlet boundary condition, and this script includes this params dictionary, which is the standard dictionary of Python, and is connected to the TCFD module or TMesh module, to any other module by the name of the parameters. And these parameters can be found in the project. So if I go to the project, okay, which is here, here's my, for example, live example. And here inside this setup file, here are all the list of all parameters which we have set in the GUI. And for example, if you would like to load this inlet boundary condition, which is the first item, so you will do it exactly in this way. So I need to go back to my where is it? I'm a little bit lost. Yeah, here. So you find the first item from inlet boundary condition free stream velocity, because it has 3 components. I would like to find the X, and because it's in the text file, so I will just transform to float, and I will store it as a speed value. And the same, I will load the T-opt parameter, which was the angle of attack, and I will load the current angle of attack value. And based on the angle of attack, I will create a rotation matrix. I will transport the speed vector. I will transform the drag direction, lift direction. So I will compute it here by the simple formulas, and then I will put back to the TCFD. So I will automatically adjust the speed vector based on the angle of attack, outlet because I'm in the free stream velocity setup. I can also adjust the initial velocity, and I will adjust the force probe direction for the drag and for the lift. So in this way I can do it. So basically you will find the parameter which define, for example, this force probe drag direction. So you will take this this string, this parameter name, and you will put it into the script in the same way, and you set first, second, and third component of the drag direction. And in this way, any T-opt simulation will adjust the speed vector based on the angle of attack. So in this way, you prepare the initial script, and then here you define just what is your minimum maximum angle of attack, how many number of samples you would like to do it for example, DOE, and in case of the optimization, you will define the maximum runs to run. So we will run a DOE to somehow to generate the graph, and the other simulation will be used to find the maximum of the optimization function. So we have done it. So at the end of the simulation, you will see such a T-opt report where we have run these all variation of angle of attack. So we have first 8 DOE values, which will give us the value of in the range from 0 to 15, and then the optimization algorithm try to find the best lift to drag ratio. And if we go to the next section, optimization function versus parameters. So here we have the blue points, which corresponds to the DOE part, and the green, which corresponds to the optimization part, and the red one is the found best point. So we can see that the drag and lift for AOA of 9.6, let's say, degrees, and the lift to drag coefficient is or equals to almost 52 for this kind of simulation. So in this way, you can done a nice analysis of the airfoil parameters within a single click, and additionally you can find some best point with respect to the lift or drag to lift ratio or any other parameter which is important to you. Okay, so maybe I'm almost done, so Luboš can interrupt me anytime or stop me because I'm too long. But basically, in this way, you can have a nice simulation. Then you can follow the data. So, for example, the velocity contours for each point. So you can go through all the results and study also or compare the flow patterns or pressure coefficients along the surface as you want, basically. So such a complex analysis can be set and done within few dozens of minutes for experts who works with TCAE every day for past several years. But you can do it within 1 or 2 hours.
Yes. Thank you, Radek, for this part. It was really nice, and yeah. So this is what it was our original intention, to show you something very simple, which almost anybody can do after a few of hours with playing with it. And this optimization part is also simple, but it really takes the simulations to the next level with optimization, I would say. If you allow me, Radek, I will take back the presentation.
Yeah, definitely.
And I would like to ask the audience to ask your questions. So far we haven't many representative questions we would like to talk about during the webinar. So we hope you will save us with your questions. So please ask your questions. We'll be happy to answer. That there are no stupid questions. There are only stupid answers. So don't worry. Ask about anything. We will do our best. And yeah. In the meantime, I played with my formula a little bit, but the model is unfortunately very, very coarse, and I haven't found anything particularly nice. Yes, we could definitely change the color, but still, yeah. So yeah, I would like to ask the last time. This is the last call. Please ask the questions. Otherwise, we will run away. I haven't prepared anything. Of course, people often ask about the compatibility with OpenFOAM. Maybe we can say a little bit about this. So TCAE is based on OpenFOAM, and on the background, it only runs OpenFOAM. It writes down all the necessary configuration files, and also all the basically these configuration files, and let the OpenFOAM work. TCAE also includes a lot of libraries and applications we have developed here at CFD Support. So it's not just an OpenFOAM, it's so much more. We are like, as mentioned in the presentation, more than 40 years aggregated of team development is included. So we have developed new boundary conditions, new function objects that evaluate everything during the simulation and let the graphical interface display all the stuff. So in these terms, TCAE is absolutely complete and sophisticated, unlimited working software where 100% of all steps and all actions can be done in graphical interface, or it can be done in terminal. So it's up to the user. Of course, on cluster you will run on terminal, but the case settings is most likely will be done in Windows. So I am now, for example, in Windows. So the graphical interface in Windows is exactly the same as the one in Linux. For normal project work, we work in Linux, of course, here at CFD Support, but I guess you know that most of the users prefer using Windows. So the workflow is exactly the same, and we believe that we are offering a huge value for the users, because all those who played with OpenFOAM before, they know how difficult it is to maintain the projects, save the projects, load the projects, keep the new version, maintain everything. So we believe TCAE is perfect tool to be effective in simulations, and also we believe it's affordable for all those who deal seriously with simulations. Okay, I'll be honest with you, I can't see any relevant questions we would answer here. So Radek, what do you suggest?
Yeah, I suggest to slowly conclude. From my experience, I also have the most question after the webinar I am attending.
Yes.
So
and
you can contact
it's
us
actually
afterwards. So
it's actually a good point, Radek. So okay, fair enough. So I will conclude with my very favorite point, that the great software is one thing, but but it's the technology, right? But it's only 40% of success, right? The rest is your skills, your effort, your experience, patience, dedications, and your willingness to succeed. So you have to maintain everything, not only the software. And yeah, the Q&A is today, let's keep it empty. Maybe this is the first time over like 85 webinars we did. So let's keep it open, but it's only an invitation for you. We would like to invite you to ask your questions. Really, send your questions anytime later, and we'll be happy to answer them via email. And you can be sure that we will never leave anyone behind, because we are CFD support. We love our job. We love all those simulation tasks, and we are engineers, and we love solving problems. Am I right, Radek?
Yeah, absolutely right.
Yeah. And one last thing, let's show ourselves. Let's show ourselves
Okay.
on camera. Let's show ourselves. Is it
We are
coming?
still here.
I can't see anything, but I believe
Yes,
that
we
the
are there.
technology
We are
works.
there.
I believe it. I believe you can see us, and it's time to say goodbye.
Yeah. Goodbye, and have a nice, smooth, and fast convergence in the CFD
Yes, and
field.
let's keep in touch and come anytime. We leave
Yeah.
you with that. Thank you for now, and bye bye.
Have a nice day. Bye bye.
Bye bye.